All right, so one interesting thing that we can do with some of the material that we've learned is we can take functions of matrices. So as an example that we can verify independently, I've always liked the square root function. So suppose that we're asked to find a matrix that can be considered the square root of this matrix. Now, one approach that people might take consists of writing down the most general 2x2 matrix, A, B, C, D, squaring it, and demanding that it equals this. Now, that's fine, but it will lead to 4 nonlinear equations in 4 variables, which you may or may not want to have to actually solve. Okay? I don't want to solve that. I'll just come right out and say that. So I'd like to see if maybe there's an easier way to approach this problem. Now, one very common technique that is used to approach a new problem is to see if maybe we can turn it into an easier problem. Okay, so let's see if we can think of an easier problem that's along these lines. So what if we had same thing, but the matrix was different. The matrix was this one. Now, what do you guys think? Could we write down an answer? I mean, I think for this one, it's pretty clear that that one will work out just fine. All right? That's not going to be a mess to write down. And it's pretty obvious that if you square this matrix, it will give that matrix. Okay? So, what could we do to turn the given problem into a problem that looks more friendly? Like that. I mean, the only difference between the given problem and the friendly problem is that the friendly problem has a diagonal matrix. So maybe we should set about diagonalizing this matrix. Let's see if we can do it. I'll need eigenvalues and eigenvectors. So I'll say, well, I could write out the determinant of A minus lambda I if I wanted to give me a quadratic, yada, yada, yada. I could also just take the trace, which is the sum of the eigenvalues, and the determinant, which is their product. So the sum is going to be 5. The product negative 14 plus 18. So, I mean, can anybody think of 2 numbers whose sum is 5 and product is 4? 1 and 4. Wow, those are easy. So let's find the eigenvector associated with 1. We'll subtract the identity. So it'll be 6, 18. So that's our first eigenvector, where we just row reduced and found the null space, and it was just real fast, okay? How about 4? Well, now it's going to be 3, 18. All right? So what we really need from these eigenvectors is a change of basis matrix. That's what we really need. So I'm just going to write down our change of basis matrix P. All right? So now, what does this mean? Well, we know that D, my diagonal matrix, is equal to P inverse A P Okay? Now, at this point, it's very helpful for us to think philosophically about the meaning of this relationship. This is a similarity transformation. We can think of R2 as sort of existing in two separate worlds. R2 in the E basis and R2 in the B basis. Okay? Every matrix that transforms R2 in the E basis to R2 in the E basis, like matrix A, has a counterpart matrix that performs the analogous transformation over here in the B basis. Okay, every matrix does, not just matrix A, every matrix. The only thing that was special about matrix A is that the B basis consists of its eigenvectors. We didn't have to. There's an infinite number of similarity transformations that we could make. We just chose this particular B basis. Okay? So every matrix over here in R2 in the B basis is associated with a matrix over here, R2 in the E basis. So from this perspective, we can say the square root of D could be taken as that matrix in the B basis. So its analog in the E basis would just be obtained by transforming it to the E basis. Now, what people don't like about this, when they look at these two equations algebraically, is they don't like that the square root didn't go over the P inverse and the P. But of course, philosophically, we understand that that wouldn't make any sense. The purpose of P inverse and P is to change the basis. It doesn't have anything to do with the operation that we're doing on the matrix. It's just taking us from one basis to the other. And it's going to do that in the same way for every matrix. All right? But that doesn't always convince everybody. So in this particular application, I have a maybe more satisfying way to indicate why I don't have to put the square root on top of the P inverse and the P. The philosophical way will still be important because I won't always be able to use this algebraic approach, but it should help to quell some of the anxiety you may be feeling about the fact that we did not put a square root over the P inverse and the P. Okay? If I multiply the square root of D by itself, over here, I'll get P inverse square root of A, P inverse square root of A, P. All right, I literally just wrote this matrix next to itself. And this is P inverse. So that's the identity. That's going to go away. Square root of A, we get A. So that's another way that you can understand why it is that this is sort of kosher. This is okay for us to do this. But philosophically, it's because the purpose of these change of basis matrices was literally to change the basis. Okay, they're not associated with the operations that we're doing on the matrix. At any rate, this immediately gives us an expression for the square root of A. it's going to be P square root of D P inverse. All right, what's my inverse? 1/3. Swap, negate. All right, and then that's going to be BE. So what do we got? Oh, I forgot my 1/3. All right. So that's going to be the top row and then 2 times the second row. So we'll have -3 plus 12, -18 plus 36, 1 minus 2, 6, 6. So the claim is that this matrix acts as the square root of that matrix. Boy, it sure don't look like it. I mean, this doesn't look like the square root of the matrix. But looks aren't the only thing. In fact, they're nowhere near the most important thing. What matters is that it works. So let's see if it works. So I don't need these anymore. All I need is my beautiful change of basis matrix. So we've got 1/3. I'm going to move that 1/3 inside to make the numbers easier. 3, 6, -1/3, 0. 3, 6, -1/3, 0. Boy, this sure don't look like it will work. Maybe we don't even need to try it, do we? It's not going to work. But I mean, 9 minus 2, that's 7. Here I got 18.
There's no way.
So that's minus 1. And what do we got here? Minus 2. That's not the... Oh, that's kind of neat. Now, obviously, we could also use negative this matrix, because if I put a minus sign in front of the whole thing, I mean, I'm going to square it, right? It's going to give me the same matrix. It might be surprising that we could get a completely different matrix by doing this. If I only change one of the signs, it will still work, but all the interactions are going to be different here. Instead of this matrix, that was a -2. That means it's going to be -2 times there and there. All right? And so what we'll get is 1/3 again, -3 minus 12, -18 minus 36. 1 plus 2, 6 plus 6. Amazingly, the 1/3 cancels out. That doesn't usually happen. But our other matrix that could be thought of as the square root of that matrix is -5, -18, 1/4. Boy, that sure doesn't look like the square root of that matrix. I mean, there's no way this is going to work.
Dr. Osborne, you're making a pretty good impression of all of us doing math right now.
So it'll be 25 minus 18. That's a fluke. Let's see, it'll be 90 minus 4 times 18. Hey, so that's 90, which is 5 times 18, minus 4 times 18. That'll be 1 times 18, right? I'll get negative 5 plus 4. And then I'll get negative 18 plus 16. Hey! All right. So I think that's an interesting application of diagonalization. I've always liked it because it has an independently verifiable result. We can square the resulting matrix and see, convince ourselves that in fact it is the square root. But we can take all kinds of other functions of matrices using this process as well. In fact, all we need is that the function is defined at each of the eigenvalues of the matrix. That's it. I don't need it to be defined between the eigenvalues. I don't need it to be defined. It could even be undefined at every other point except the eigenvalues. And I can do the function of the matrix using this. We could use this technique to find an inverse matrix. We'll just use the function 1 over x. So I always thought that was neat.